Hello, this is Daniele Ciani from the National Research Council of Italy, and I am presenting a study on the ocean surface currents and temperature reconstruction through deep learning algorithms. Ocean currents are a crucial variable to understand the variability of the ocean, but also of the planetary atmospheric boundary layer, and also their high resolution spatiotemporal monitoring is crucial for practical applications like fishery, ship routing, and safe navigation. Currently, the monitoring of the ocean surface currents is provided by constellations of radar altimeters that observe the ocean surface along one-dimensional tracks as depicted on your left. This information is then interpolated in order to get two-dimensional absolute dynamic topographies, from which in the end we derive the surface geostrophic circulation as depicted on your right. Unfortunately, this observation methodology is limited by the assumption of geostrophic balance and also by the nadir-looking radar altimeters sampling strategy, which results in altimeter-derived products with effective resolution around 100 kilometers and 10 days, including the mid-representation of mesoscale to sub-mesoscale dynamical features, which makes very challenging all the aforementioned applications. Our aim is thus to extract dynamical information contained in independently observed high-resolution tracers as sea surface temperature in our study, to extract dynamical information and improve the altimeter-derived surface currents estimates. So here we use convolutional neural networks that are built to learn an end-to-end mapping methodology between low-resolution and high-resolution images. This is operated applying convolutional filters that firstly extract features from the low-resolution image, let's say our starting point, our satellite observation, then remap these features onto a high-resolution image, and in the end reconstruct the high-resolution output. The learning is formally performed through a minimization of the error between our prediction and a ground truth, which has to be known a priori. Here we show the baseline convolutional neural network formulation proposed by Dong and colleagues in 2016. Here you can still recognize the structure of the convolutional neural networks proposed by Dong and colleagues in 2016, but in particular, building upon the work of Bongiorno Nardelli and colleagues 2022, we consider 6 predictors as an input to the convolutional neural networks that include the low-resolution ADT and SST, the ADT and SST measurement uncertainties, but also the SST temporal derivatives and again the uncertainty on this SST temporal variation, while as an output we consider the high resolution SST and absolute dynamic topography. Here we provide an outlook of the workflow explaining our experiment. So starting from 1 year of numerical model outputs for the Mediterranean area during the year 2017, we extract satellite equivalent absolute dynamic topographies and sea surface temperatures. These quantities are then combined together exploiting the convolutional neural network architecture that we showed previously. So we are in this way able to perform an observing system simulation experiment in which the performances of the network are evaluated directly, comparing our results with model-derived ground truth, which are basically 40 days of our 1 year long time series, which are kept apart for performing the independent test. And then we apply our neural network model directly to the reconstruction of satellite-derived ADT and sea surface temperature with the aim of enhancing the features that are found in the satellite-derived dataset. The evaluation, the assessment of the exercise in this case is operated through collocation with in situ measurements. The satellite equivalent ADT and SSTs were generated starting from the model outputs. For ADT, subsampling the model surface height as a constellation of 4 radar altimeters. For SST, injecting realistic clouds in the model-derived sea surface temperature, and then reconstructing the satellite equivalent level 4 fields, including the formal mapping error for both quantities, via objective analysis. Here on the left, you can recognize our convolutional neural network architecture as it runs after testing several different architectures. This is a small update compared to the architecture proposed by Buongiorno Nardelli and colleagues in 2022. In particular, we consider 6 predictors instead of only 4, as done in the previous reconstruction exercise. And we have 2 targets, as announced at the beginning, so the joint reconstruction of a high-resolution ADT and sea surface temperature. To first assess the improvements of this new architecture compared to the results published in 2022, we can compare the ability of the neural network to produce high-resolution absolute dynamic topography with respect to, let's say, standard altimetry, so standard satellite products. This is expressed by the red areas in the maps provided on your right. So the red areas are areas of improvements. In the previous study of 2022, you can recognize a very extended area of improvement with very few spots of degradation. In the new configuration, which is the one exploiting the joint information from ADT and sea surface temperature, also in the production of the outputs, you can see a significant further improvement of the performances. And this is also due to the possibility of tuning the loss function through which the neural network is trained in an innovative way that accounts simultaneously for absolute dynamic topography and sea surface temperature with relative weights. Here you can compare at the same time the performances of the convolutional neural networks in reconstructing the ADT in the left column, as we discussed in the previous slide, but you can see at the same time also the capacity to reconstruct SST. Overall, we can recognize an improvement area that dominates our Mediterranean basin, although the basin is also populated by a few spots of degradation, as indicated by the blue areas. We go on with the assessment of the super resolved currents reconstructed from satellite-derived data using the neural network trained with model outputs. Again, here red and blue boxes stand for improvement and degradation areas based on in situ measurements. For the surface currents, we still have to work in order to get an improvement in the entire Mediterranean basin, at least based on this 10 years long reconstruction from 2008 to 2019. But already comparing our present day results with the one of Buongiorno Nardelli and colleagues 2022, we start identifying more clearly some improvement areas, for instance, in the Levantine Basin, in the southern Tyrrhenian and in the western Mediterranean Sea, for both components of the motion, for the zonal and the meridional flow, which means the joint ADT-SST reconstruction brings benefits for the description of dynamical feature in the Mediterranean basin. So in the framework of the ESA of world ocean circulation, we primarily focus on ocean currents, but we are presently trying to evaluate the goodness of the higher resolution reconstructed sea surface temperature, again via collocation with in situ observations. And as a short-term perspective for this work, we are looking forward to collect observations from the surface water and ocean topography high resolution mission as soon as they will be available for the scientific community. which will enable a training of the neural network uniquely based on satellite observations without going through the observing system simulation experiment phase, in combination, for instance, with the Sentinel-3 SLSTR system phase temperature observations. Thanks very much for your attention.